Comet 3I Atlas, the third confirmed interstellar object, is currently on a dramatic trajectory toward the Sun. It's hurtling through the inner solar system, having crossed Mars's orbit and accelerating to nearly 68 km per second as it approaches its closest point to the Sun. However, as the world's telescopes prepare for a mid-October solar conjunction, Atlas will become invisible, plunging into the Sun's intense electromagnetic field. This leaves scientists with more questions than answers about its peculiar chemistry, immense size, and unpredictable behavior. What happens when a potentially 50 kilometers object from another star system collides with the solar wind at such high speeds, hidden from human eyes? The timeline, risks, and mysteries begin now. This cosmic wanderer is carving a unique path inside Mars's orbit, tilted about 5 degrees off the ecliptic. Its steep retrograde trajectory slices almost head-on through the solar system's plane, with an orbital inclination of 175 degrees, highlighting its foreign origins. Most comets and asteroids move in the same general direction as the planets, but Atlas is an outsider, approaching from the opposite direction at a sharp angle. Its acceleration is relentless. First clocked by the Atlas survey in early July at 58 km per second, its speed is now steadily climbing, projected to reach almost 68 km at perihelion. Imagine a chunk of interstellar debris, possibly the size of a medium city, racing through our solar system faster than any spacecraft ever built. At this speed, it could cover the distance from Earth to the Moon in just over an hour. Perihelion is set for October 29th at 11:55 UTC, with the closest approach to the Sun occurring at about 136 to 140 astronomical units, inside Mars's orbit, but still well beyond Earth's. Unlike sun-grazing comets that face destruction, Atlas will not dive into the solar corona. Instead, it will skim the boundary of the inner solar system, navigating a region where solar wind and electromagnetic fields are most turbulent. From Earth, it will be in the constellation Virgo at its closest approach, but the Sun's glare will render it completely invisible. The minor planet center's orbital elements confirm a hyperbolic trajectory with an eccentricity greater than 1, meaning it will never return. Its inbound and outbound paths, along with its sharp solar swing, indicate a brief, one-time passage. Every kilometer it travels now brings it closer to the Sun's domain, and further from any vantage point capable of tracking its journey. This is the geometry of a cosmic interloper. Inside Mars's orbit, 5 degrees off the ecliptic, accelerating from 58 to nearly 68 kilometers, with a rendezvous with the Sun on October 29th. The numbers are precise, the timeline fixed, and the window for direct observation is rapidly closing. From Earth, October 21st, 2025, marks superior conjunction, when 3I Atlas slips directly behind the Sun, hidden from ground-based telescopes and most space observatories. For several weeks, solar glare will dominate the sky, obscuring any trace of this interstellar visitor. Astronomers call this a blackout, an enforced silence where no new data can be gathered, regardless of equipment sophistication. The Sun's disk acts as a blinding curtain blocking visible light, infrared and ultraviolet signals. Imagine the frustration. After months of urgent coordination, over 120 observing runs, emergency overrides at flagship telescopes, frantic Slack channels and late-night Zoom calls, the global campaign is forced to pause. The geometry is unforgiving. Solar elongation, the angle between the comet and the Sun as seen from Earth, shrinks to nearly zero. Even the most ambitious adaptive optics or dusk-dawn observation techniques fail. Detectors are at risk of damage, triggering automatic shutdowns. The last reliable data points will trickle in around October 18th, as the object's apparent separation from the Sun dips below critical thresholds. Coronagraphs, designed to block the Sun's core, offer little hope. At magnitude 12, 3I Atlas is too faint and compact to stand out against the turbulent brightness of the corona. Deep background subtraction and stacking techniques, effective for brighter sun grazers, are insufficient here. No confirmed detections have emerged from SOHO, Stereo, Parker Solar Probe, or Solar Orbiter during this window. Attention briefly shifted to Mars in early October. Orbiters like Mars Express and the ExoMars Trace Gas Orbiter captured a handful of long-exposure images and low-resolution spectra as the comet passed the red planet. This offered a fleeting advantage, a last look before the sun intervened. Yet these datasets are limited. The coma appears as a faint fuzzy dot, the nucleus unresolved, and the tail invisible to their sensors. Debates within mission teams about redirecting Mars orbiters for perihelion phase imaging were ultimately decided by resource constraints, orbital geometry, and instrument safety. The opportunity closed. When will the silence break? The recovery window opens in mid to late November as 3I Atlas emerges from behind the sun and reappears in the dawn sky. By then, it will be receding in both distance and brightness, but still within reach of large telescopes and dedicated amateur astronomers. The next milestone is December 19, 2025, when the comet makes its closest approach to Earth, about 180 astronomical units, just before the winter solstice. Between conjunction and reacquisition, the story is one of anticipation and uncertainty. Every hour lost to the sun's glare is an hour when the most anomalous interstellar object ever recorded could transform, fragment, or simply fade away unseen. The scientific clock is ticking, and the world waits for the first signal to break through the solar curtain. The comet's size refuses to settle into a single number. Early photometric readings from dozens of telescopes suggested a nucleus between 5 and 50 km wide, potentially the largest interstellar object ever observed. This wide range isn't a rounding error. It's a symptom of an object shrouded in its own activity. The coma, a dense envelope of gas and dust, expands so thickly around the core that even the most powerful ground-based mirrors and Mars-orbiting cameras cannot resolve the true solid body. Astronomers are left to infer its mass and volume from indirect clues: how it brightens, how its light scatters, and how quickly the coma thickens as it nears the sun. Its color is also a changing story. Through June and July, the coma's spectrum leaned red, perhaps indicating complex organic grains or larger, slowly sublimating particles. By August, it shifted to a pronounced green, a hue rarely seen so strongly in solar system comets. Spectroscopic campaigns, including those with the Canada-France-Hawaii telescope and the JCMT, tracked this evolution in real time. The culprit appears to be an upsurge in carbon-based molecules, especially C2 and CN radicals, released as the comet's CO2 content vaporized under increasing solar heat. The green glow is not just a visual oddity, it's a chemical fingerprint, revealing that CO2, not water, dominates the outgassing. This alone sets 3I Atlas apart from most known comets, whose activity is usually driven by water ice. The chemical portrait grows stranger still. Spectra obtained from both hemispheres and embargoed preprints circulating among specialist teams point toward a nickel-to-iron ratio far outside typical solar system bounds. Strong, persistent nickel lines outshine their iron counterparts by margins that hint at an origin in a supernova remnant or the stripped core of an ancient differentiated planet. If confirmed, this would rewrite assumptions about what kinds of debris survive the interstellar journey. The dust itself, revealed by polarimetric studies, shows extreme negative polarization, scattering light in a way that suggests a preponderance of fine, possibly glassy or metallic grains, rather than the silicate material familiar from local comets. Its morphology is yet another puzzle. Instead of a classic anti-solar tail, 3I Atlas sports a coma that is brightest on the sunward side, with a forward scattering envelope that defies standard models of dust and gas flow. The sun-facing edge gleams with a density and texture that has sparked heated debate among observers. Some argue for a jetting phenomenon, others for a sheath of highly reflective, metal-rich dust. The anti-solar tail, if present, remains faint and elusive, a mere whisper against the glare. The light curve, obsessively tracked in the weeks before solar conjunction, adds urgency to the mystery. Instead of fading as expected, the comet's brightness climbed steadily, even as it crossed Mars's orbit and entered the sun's domain. This pre-gap brightening, recorded in the final days before the data blackout, fueled a storm of speculation across every observer channel. Was it a sign of fragmentation, a new outburst of volatile gas, or simply the unveiling of fresh surface layers never before touched by sunlight? Each anomaly, size, color, chemistry, polarization, coma geometry, has drawn the attention of a sprawling, loosely coordinated observer community. Professional astronomers, amateur sky watchers, planetary scientists, and instrument specialists have converged in digital forums, racing to decipher the object's secrets before technical limits and the sun's glare impose silence. Their findings, arguments, and unanswered questions now set the stage for a deeper confrontation with the limits of our instruments and the boundaries of current cometary science. At magnitude 12, 3I Atlas is predicted to be fainter than any planet as it sweeps behind the sun, far below the detection threshold of most solar observatories. For instrument engineers and data analysts, this number defines the practical boundary between wishful thinking and real measurement. Coronagraphs like SOHO's LASCO C3 or Stereo, his heliospheric imager, are built to block the sun's glare and reveal dramatic outbursts, but their detectors are tuned for objects at least 100 times brighter than this interstellar visitor. Even with heroic digital processing, the comet's surface brightness falls short. The comet's angular size, just a few arc seconds at best, makes it indistinguishable from the background noise of the solar corona. No confirmed detections have surfaced from any solar-focused spacecraft, not from SOHO, Stereo, Parker Solar Probe, or Solar Orbiter. The standard data products, those daily movies of the inner solar system, show nothing but turbulent plasma and the occasional planet. For 3I Atlas, the signal-to-noise ratio remains stubbornly below 1, even when stacking dozens or hundreds of images. The comet's faint diffuse glow is simply overwhelmed by the ever-changing light patterns that surround the sun. Some teams propose a workaround: shift and stack. The concept is elegant in theory. Take hundreds of images, predict the comet's apparent motion across the detector, and digitally align each frame so that any faint moving object adds up while static background features cancel out. On paper, this method can push the detection limit down by a full magnitude or two. In practice, it demands an accurate ephemeris, precise knowledge of the comet's path, and a willingness to wade through terabytes of noisy data in search of a single faint smudge. For 3I Atlas, even the most optimistic shift and stack campaigns, 100 frames from LASCO, 50 from Stereo, still fall short of a secure detection. The math is unforgiving. The expected gain in signal-to-noise is swamped by the sheer faintness and compactness of the coma. Instrument safety protocols introduce another barrier. As the comet's solar elongation drops below critical angles, automatic shutdowns kick in to protect sensitive detectors from accidental exposure to the sun's disk. No amount of manual override can justify risking a billion-dollar imager for a target that may not even be visible. For ground-based telescopes, the situation is even more stark. The sun's glare saturates the sky, and no amount of adaptive optics or horizon skimming can pull the comet out of the haze. Mars orbiters offered a brief glimmer of hope, their unique vantage point allowing for a handful of long-exposure images in early October. But by the time perihelion arrived, their orbital geometry and instrument constraints closed that window. No high-end telescope on Earth, in orbit, or circling Mars remained in position to watch the critical moment when solar heating peaked. For now, the data gap is absolute. The world's best coronagraphs and heliophysics imagers are forced to admit defeat. 3I Atlas is simply too dim, too small, and too close to the sun for any direct measurement during conjunction. The only path forward lies in creative data mining, reprocessing old exposures, stacking images along predicted tracks, and holding out hope for a post-conjunction surprise. Instrument teams are already sketching out contingency plans for future interstellar visitors. More flexible safing protocols, dedicated shift and stack pipelines, and perhaps one day, solar observatories designed to chase faint comets through the glare. For now, the boundaries are clear. The object is out there, racing unseen, and the instruments built to catch it have met their match. The moment 3I Atlas swings closest to the sun brings a new set of questions into sharp focus. Questions that stretch beyond standard cometary models. Among the most vocal are advocates for electromagnetic explanations, the so-called electric universe theorists who argue that comets are not just icy relics but dynamic players in the solar plasma environment. For them, perihelion is more than a gravitational checkpoint. It's a natural laboratory where the solar wind, electric fields, and charged dust could interact in ways that leave measurable fingerprints. One hypothesis on the table is a sudden outburst of activity, triggered not by heat alone, but by the object's plunge through regions of intense electromagnetic flux. If the comet's carbon dioxide-rich dust is electrically charged, the sun's field could accelerate particles, alter the comet's shape, or even shift the trajectory by a detectable margin. Effects that would show up as small but real deviations in post-perihelion tracking. Dusty plasma specialists are already drafting diagnostic metrics: changes in coma polarization, unexpected drifts in the outbound path, or a burst of radio emission as solar wind slams into the dense metal-rich envelope. No one is claiming certainty. These are testable predictions, not declarations. When 3I Atlas reappears in November, every new data point, brightness, position, coma structure, will serve as a diagnostic for mission planners and alternative theorists alike. The next phase is a waiting game, with the hope that nature might deliver a verdict on ideas long considered fringe. Astrologers tracking the sky at perihelion note a rare convergence. As 3I Atlas threads the constellation Virgo, it stands in direct opposition to Chiron, with Eris nearby, while Jupiter and Pluto form their own axis across the heavens. Chart watchers read these alignments as a grand cross overlaid with kite and grand trine motifs, patterns long associated with crisis, transformation, and the search for deeper purpose. Some interpret the comet's passage through Virgo as a symbol of healing through disruption, a reminder that even the most alien visitor can stir ancient patterns of reflection and renewal. For those who follow planetary cycles, the timing resonates. 3I Atlas makes its closest pass by Earth just before the winter solstice, a season marked by darkness turning toward light. The outbound journey brings the traveler into a close encounter with Jupiter by March, a progression that in astrological tradition hints at the possibility of new beginnings and shifting collective priorities. Whether these patterns are read as cosmic metaphor or simple coincidence, they offer a bridge between scientific observation and human meaning-making. For viewers who want to mark the occasion, a commemorative design is available. The story of 3I Atlas continues, woven from both data and dreams. As the world waits for its return to view, key questions persist. What drives its anomalous behavior? Will perihelion trigger changes in activity or trajectory? These answers await its reappearance in mid to late November. As the data gap continues, each new observation of 3I Atlas will test our understanding of interstellar visitors and the limits of solar system science. For now, only the archival record stands, a reminder of how much remains hidden, even as the evidence grows.